I mean, is this intentional or?
Yeah, I think it can come during
Okay.
the talk. Yeah, though I was not very sure about it, so I did not include it in the slide. Visible, right?
Yeah, perfect. Yeah.
Okay, I think Guhan, please go ahead and welcome the speaker.
Okay, so welcome everyone to this mathematics colloquium at Ashoka University. It's a great pleasure that Professor Anandavardhanan, UK, a very distinguished mathematician from the Indian Institute of Technology in Bombay, is here with us, and he'll speak on orthogonality of invariant vectors. So over to you, Anand.
Okay, so thanks so much, Guhan and Gaurav, for this invitation to speak at Ashoka. It would have been wonderful if I could visit your beautiful campus, but another time.
Soon.
So yeah, soon, I hope, yeah. So the title is Orthogonality of Invariant Vectors, and so mostly I'm not going to get into our own work, but the results will come at the end. Except for the results, mostly it will be a general talk on basic representation theory. And the result which I'll state towards the end is a joint work with Arindam Jena, who's a postdoc at TIFR now. So, okay, so let's start. So Guhan, you said maybe some students are also there, right, in the audience? Yeah. So, so let's start with something very, very basic. So suppose you have two groups, G1 and G2, and consider, a map from G1 to G2, and the correct kind of map between the groups, which means it respects the group structure. So phi of xy is phi of x times phi of y. And as all of us know, we call such a map a homomorphism from G1 to G2, right? So, so the point of representation theory is to understand groups a bit more, and we are dealing only with finite groups today. And so this is what a homomorphism is. And now we are going to consider homomorphism between two groups. One group is given to you, a finite group G is given to you, and this is my G1, and my G2 is this particular group. So this is complex numbers, C star, so that's non-zero complex numbers, and that's a group under multiplication of complex numbers. And consider your left group to be G and the right group to be C star. And if you consider a homomorphism, it has a special name, it is called a character. So the word character is going to come twice, one as these one-dimensional representations, homomorphisms into C star, and one more way the word character will appear after a few slides. And in fact, long ago, in the early 1800s, Gauss did work with characters of certain finite abelian groups. In fact, this word, all of us know what is called the Gauss sum. So a Gauss sum is basically you take a finite field and you consider its additive characters valued in C, the additive group of C, and you consider the multiplicative group of your finite field and consider its multiplicative characters and mix it together, take a sum over those. So Gauss had very famous results on the Gauss sum, and this was around 1805, 1810, around that time. So characters were anyway being employed at that time. Okay, so, and especially characters of abelian groups. Okay, so a representation, which is our basic topic today, a representation of a group is a generalization of the notion of a character. So why is it a generalization? Because for a character, we were taking a homomorphism from our group G to the group C star, and C star, let me write it as GL1C, meaning one by one matrices which are invertible. In other words, just non-zero complex numbers. Okay, so a representation would be, so this was the right side of that homomorphism. This was the codomain of that homomorphism. And now you take a homomorphism valued not in GL1C, but GLNC, where n is any natural number. And that is what is called a representation. So what is this group on the right-hand side? If there are undergraduate students in the audience, this is a set of all n by n matrices with complex entries, invertible. So determinant is non-zero, and then they become a group under matrix multiplication. So these are all n by n matrices, n by n invertible matrices, determinant non-zero, and they form a group under multiplication. That group you fix on the right-hand side, and you consider homomorphisms of your given finite group, and that is what is called a representation. Okay. So for those students who know the notion of a group acting on a set, maybe a better way to define a representation is just to say that it is a linear action of the group on a vector space. So in general, in mathematics, if you have a difficult problem, you try to linearize it. In some sense, this is what, in order to understand groups better, you study how groups act on various sets and what are the best kind of sets that you can think of, sets with additional structure. So one good object to look at, where you can look at the action of your group, is a vector space. And because it's a vector space, you also demand that your action is also linear. So in other words, so pi comma v is a representation of G. So pi is the action and v is the space where the group is acting, the vector space where the group is acting. It's a representation of G. If for each G and G, each group element, you have an action on V, which is also a linear transformation. It respects the vector space structure. So pi G is a linear transformation. And moreover, pi of G1, G2 is composition of these two operators, pi G2 followed with pi G1. And you also demand that the identity element of the group, pi at the identity element, is the identity linear operator, the identity transformation. Okay, so this is, once you fix a basis, this is exactly our earlier definition. If V is n-dimensional, then pi G will be an element in GL and C if you fix a basis of V. If you fix another basis, it will be something conjugate. Okay, so this is what a representation is. And here is the word character coming once more. So I'm going to define a map chi pi from G to C, not C star, but C. It could be 0 also. And this is the character of the representation. So as we saw, pi G will be an n by n matrix for some n. And it's an n by n matrix, and you take its trace, sum of diagonal elements. And that will be maybe 0, maybe non-zero, anyway, a complex number. And that is called the trace of the representation. I mean, the trace, this is called the character of the representation. So this is called the character of pi. So in particular, if pi is one-dimensional, this notion of character is same as the earlier notion of the character, because trace is doing nothing, right? It's a 1 by 1 matrix. Okay, so we have defined representations over the field of complex numbers, right? Throughout here, I was taking C. My V was over C. And my matrices were with complex entries. So that's the meaning of saying these representations are defined over the field of complex numbers. But there's no need to fix complex numbers. You could also look at representations over other fields. For example, people like Guhan, Venkat, might look at other fields. They may be interested in finite fields or algebraically close fields of characteristic P instead of complex numbers. That's possible. So you could also look at representations of over other fields. And in particular, if we take the field to be FP bar. So FP is the finite field of P elements, Z mod PZ. And bar is, you fix one algebraic closure. And if you take your field to be the algebraic closure of the finite field of P elements, then this theory is called the representation theory of finite groups over FP bar. It's called P modular representation theory. Because you're fixing a P, you're considering finite field of P elements, and your vector spaces are defined over there, and there you are looking at the group action, and that is called P modular representation theory. So the modular representation theory and complex representation theory. So complex representation theory is also called ordinary representation theory. These are almost the same theory if your P is such that P does not divide the cardinality of your group. Okay, so G is a finite group, it has a certain cardinality. And if P is a prime number which does not divide that cardinality, then P modular representation theory and characteristic zero representation theory are almost the same. In fact, exactly the same, all the theorems go through. But things become very different if P divides the cardinality of the group G. And then modular representation theory is a very different animal. It behaves very differently. Okay, so part of the result that with Arindam that I want to describe towards the very end of the talk, it is a question about ordinary representations of finite groups. In fact, we will be looking at one particular group, very, very simple group. And the question is about complex representation theory. But part of the interest in this result is that we are not able to answer the question purely in the realm of complex representation theory. And we have to use P modular representation theory in order to, come with some kind of an answer. So this theory is, so up to now, what I have said is there is ordinary representation theory dating back a couple of centuries. There is also P modular representation theory, again, very old, but much after characteristic zero theory. And we are going to look at a specific question in ordinary representation theory, but we are not able to answer the question using only ordinary representation theory. And we are forced to use some modular representation theory in order to answer a classical representation theory question. Okay, so we will reach there. Let me give some history. Some important names in representation theory. First and foremost, Frobenius. This name is they're everywhere in representation theory, omnipresent. So Frobenius, and I think Schur was Frobenius's doctoral student, Isai Schur. And another name that comes very much in character theory and representation theory is Burnside. And then Richard Brouwer. Of course, Brouwer is famous for many things. So you can see, generation-wise, this is a bit later. Brouwer is a bit later. And the first three, Frobenius, Schur, and Burnside, they are all in ordinary representation theory, meaning complex representation theory or characteristic zero representation theory. And Brouwer is the one who developed P modular representation theory, when P does not divide the cardinality of your group. So Brouwer is different, and it's a bit later, as you can see. So these are the famous people. I mean, of course, there are many more people, but if one has to name four distinguished names from classical representation theory, the highlighted three from characteristic zero and Richard Brouwer from characteristic P. And so I did not name these on my own. This is what everyone mentions. So for example, here is a famous book by Curtis, and it's titled Pioneers of Representation Theory, and the subtitle is Frobenius, Burnside, Schur, and Brouwer. And I guess the pictures must be in that order. So this is Frobenius, this is Burnside, Schur, and Brouwer. So maybe my order was different. Yeah, Burnside and then Schur. Yeah. Okay, so that's a little bit of history. Maybe a little bit more I will continue. So Frobenius, I am putting a year 1896, and Richard Brouwer, I am putting a particular year 1937, because it's in 1896 that general representation theory, somehow Frobenius dreamt of it or worked it out or whatever. In fact, I saw this particular quote while preparing for this talk yesterday evening. It's from a historical note by Keith Conrad on his website. So this is a German paper, and this is, I guess, Conrad's translation. Paper is from 1896, and he says, in April of this year, Dedekind gave me an exercise whose solution, which I hope to be able to present soon, led me to a generalization of the notion of a character. So this notion here is the notion that I introduced in the very first slide. So here character just means it's a homomorphism valued in C star. Okay, so notion of a character to arbitrary finite groups. And I want to develop this notion. So this is going to be either, a representation, a homomorphism into GLNC, or the character of that representation. By generalization, one could take trace of a representation. So character of a representation. So generalization of the notion of a character to arbitrary finite groups. I want to develop this notion here since I believe that by its introduction, group theory should undergo a major advancement and enrichment. And 1896 is many years ago, so 120 years ago, and it is true. So 130 years ago, roughly, and it is true that we know that it did change the face of group theory, it did change the face of number theory, it did change the face of harmonic analysis, many branches of mathematics. So this is Frobenius. And I also put it here to Brouwer because modular representation theory came up around mid-1930s. In fact, the very first paper, a famous paper of Brouwer and Nesbit. I guess Nesbit was at that time a PhD student of Brouwer. And that is the first paper in P modular representation theory when P does not divide the cardinality of G. And that paper is from 1937. So there's a gap, but not all that. Okay, 40 years is a big enough gap. And so modular representation theory is slightly modern compared to ordinary representation theory, but still very old. And I will put 3 quotes. So the first paragraph is one quotation. This is from somewhere else, and this is from somewhere else. All from the introduction of this very famous book by J.P. Sayre, Jean-Pierre Sayre, titled Linear Representations of Finite Groups. And this is a classic book. First edition was in 1967. And the book has 3 parts. The first part is very basic characteristic zero representation theory. The second part is again characteristic zero theory, but slightly advanced topics. And the third part, what he calls Brouwer theory, which is exactly the P modular representation theory. So the only reason for me to quote this, okay, maybe 2 reasons. One is that, representation theory is a very powerful tool, not just in various areas of mathematics, but also in physics, also in chemistry, in various other sciences and engineering. So I thought if there are undergrad students who are taking all these things, I would stress that, this is something which has turned out to be very useful in various areas of human endeavor. Of course, I have no idea at all of chemistry or physics, but let me quote Sayre. So the first part of the book was originally written for quantum chemists. It describes a correspondence due to Frobenius between linear representations and characters, a fundamental result of constant use in chemistry, in physics. Then I have tried to give proofs elementary, etc. And then the third part is the P modular representation theory, which is much more advanced than the first part. And then he also says, I take pleasure in thanking somebody, and Josiane Sayre, who is Sayre's wife, who have authorized me to reproduce part 1. So who is a well-known chemist, quantum chemist, Mrs. Sayre, Josiane Sayre. And so he wrote the first part of this book as lecture notes to his wife's students in quantum chemistry. And then he thanks her and one of her colleagues for authorizing him to reproduce part 1 as part of this book. Okay, so so here is a nice picture. So Josiane Sayre does not have an English wiki page, but there's a French wiki page, and this photo is from that page. This is Oberwolfach in 1949. You can see the Oberwolfach symbol here, and this is Sayre, and this is Josiane Sayre. And once again, if students are there in the audience, one of the most important mathematicians in the history of mathematics, maybe, 1926 born. So he's like, how many years? 96 years, 95, 96 years old. And Josiane Sayre passed away in 2004. Okay, so Guhan, this is why I had the Google, the Wikipedia page here. I hope I'm not being frivolous, but I will make a comment. So Wordle anyway is a craze these days. And in the Wikipedia page, you can see its history. The first line, maybe the font size is too small. But when I put this photo, it did occur to me that there is something here. So Wordle is invented by Waddell, who initially created the game for himself and his partner, Palaksha, I don't know how to pronounce, but yeah. So, so the only thing that I wanted to say is, true work is, a work of love in all its, in all its senses. So how do I go back to my PDF? Yeah. So here too, because he wrote this first part for his partner students, and just as a work of love, in the sense love for his own mathematics, and maybe for his partner and her students. And this is the most famous book in representation theory. And when I put this photo, I was reminded of this recent sensation of Wordle, and I did see this line that was why that was the origin of Wordle also. Okay, so to continue, let's little bit come back to, get back to the real results of this talk. So our setting, this is me and Arindam. So where is our title coming from? So there is orthogonality of invariant vectors. So vectors, that means there is some vector space. Of course, we are in representation theory, so there is an underlying vector space where your group is acting. And invariant, so invariant means what? There must be some action, maybe by the group itself, maybe by some subgroup. And if a vector is invariant, that means there is some vector which is not being changed when the group is acting. So invariant vectors is in plural. So maybe there are two subgroups, and I'm taking vectors invariant with respect to one group and invariant with respect to another group. So you have got two vectors, and these are finite dimensional vector spaces. There are natural inner products there. And under those natural inner products, you can ask the question, these natural vectors that you have, are they at 90 degrees or not? So orthogonality of invariant vectors. So where is this coming from? It is from this. So we are so right now the group G is any finite group for the next few slides, and then when we come to our result, we will focus on one particular group. So I'm introducing the word irreducible here. Those who know it. Otherwise, in mathematics, whatever you study, there will be some structures and there will be some basic building blocks. So so if you are doing modules, you will look at simple modules, and then everything is constructed out of that. Whatever you look at, maybe simple groups in group theory. So similarly, all representations are built out of these basic representations called irreducible representations. Let's leave it at that. Those are the basic building blocks. So we could, as well, any problem, we could focus on irreducible representations. So you have an irreducible representation of a finite group G, and suppose you have a subgroup H. And in this representation of G, you take a vector V, and it is called H invariant. So pi H is my action, and if pi H V, so pi H V, because it's an action, pi H V will be some other vector in V. But suppose, this particular vector V has a property that it doesn't change. It is fixed under this action. And if this happens for all elements in your subgroup, whatever H you take, if pi H leaves V fixed, leaves V invariant, then V is called H invariant. So very natural definition. And the subspace of H invariant, you can easily see, because pi H is a linear operator. If V and W are H invariant, then V plus W is H invariant, and any constant multiple of V is also H invariant. So H invariant vectors form a subspace, and that subspace is usually denoted by V upper H. So this is a space of H invariant vectors, which may be zero. There may be no non-trivial H invariant vectors. There may be a lot of H invariant vectors. So all these are possible. This is some generality that we are discussing now. The notation is VH. So now let pi V be an irreducible representation of G such that I have two groups that I consider, H and K. And suppose you also know that pi has this property that the space of H invariant vectors is non-zero, but it's not too large either. It is only one dimensional. So any two H invariant vectors differ by a constant. Similarly, K is another group, and you look at all K invariant vectors. And suppose you are in a situation where pi has the property that any two k invariant vectors also differ by a constant. That means up to scalar multiplication, there's a unique H invariant vector, let's call it VH, and a unique K invariant vector, let's call it VK, up to constant multiple, up to scalar multiplication. Okay. Now that you know up to scalars, you have these two natural vectors, you could ask this question: what is the angle between them? What is the inner product of those two? And we also know these are finite dimensional vector spaces. Up to scalar multiplication, there is also a unique G invariant inner product. So you can take the standard inner product and you can make it G invariant by an averaging process. And that is unique. That is because unique up to scalar multiplication. That is because of this basic result in representation theory called Schur's lemma. So Schur's lemma, it's an easy consequence of Schur's lemma that inner products, G invariant inner products on an irreducible representation, any two will differ by a scalar. So that's also unique. Everything, all these three up to scalars. Now that you have a unique H fixed vector and a unique K fixed vector and a unique inner product, all up to scalar multiplication, you fix one. So let's denote it by this inner product with respect in pi. And you know, I don't want ambiguity of scalar multiplication either. And one way to do that is, you know, you make it norm one. You have already fixed an inner product. In that inner product, you make VH and VK norm one. Okay. Now, you know, if you have a VH and if you have a scalar multiple, because you have taken norm one, you know that that scalar has modulus one, right? Earlier, it could have been any two could have differed by any complex number, but now I'm looking only at norm one vectors, so that scalar will be of absolute value 1. And so with all these things, you can define the following object, and this was considered by Benedict Gross in 1991. And for all compact groups, you can consider this. What he calls the correlation coefficient of H and K in G with respect to pi. And this is nothing but this angle, this inner product. You take modulus. So as you can see, you know, VH is unique only up to a multiple of absolute value 1. But if you have, you know, instead of VH, if you have C times VH, C comes out, but you are also taking absolute value and mod C is 1. So that doesn't matter. Scaling doesn't matter here now because you have assumed VH is of norm 1. Scaling doesn't matter. Similarly, scaling doesn't matter here. Okay. And inner product also, you have fixed the inner product and only after that you are making norm 1. So that scaling also doesn't matter. So conclusion, this is a well-defined quantity. This is a well-defined quantity. Under this assumption that the dimension of H invariant vectors is 1, the dimension of K invariant vectors is 1. So this is called the correlation coefficient of H and K in G with respect to pi. Okay, so this is well defined. That's a simple observation. And this seems to be a very interesting thing to look at. And in particular, we can study this correlation coefficient, which is telling you what exactly the angle between these two vectors is, not just whether they are orthogonal or not. In particular, VH and VK are orthogonal if the correlation coefficient is 0. So one is interested in looking at this correlation coefficient. It's a 1-hour talk, no, Guhan? Yeah. So now, you know, let me introduce one more word. How do you get enough examples where correlation coefficient is a good object to study? So what I wanted here was this particular property. You have two subgroups such that the H invariant vectors and K invariant vectors, both these are one-dimensional. And a little bit more you can demand, and there are many examples of groups with that property. So a subgroup H of a finite group G is said to be a Galvan subgroup if the H invariant vectors of your representation, its dimension is either 0 or 1. It's less than or equal to 1, but this happens for all irreducible representations of G. So earlier I said pi has the property that dimension VH is less than or equal to 1. But suppose for all irreducible pi you have this property, then H is said to be a Galvan subgroup. And in particular, if you have a group G with two Galvan subgroups H and K, then probably you have many examples of pi for which the correlation coefficient is an interesting object to be investigated, right? Because it's Galvan, and there are many examples of Galvan subgroups, and then, you know, dimension is less than or equal to 1. So you can probably hope that if it is less than or equal to 1, then, you know, it may not be the case that all of them are 0. A lot of that turns out to be 1 also. So probably you have many interesting representations where this coefficient can be looked at. Okay. So sometime, and I was not aware of either this coefficient or these questions, though it's a very famous paper of Negroes. In fact, I might even have looked at that paper, but this comes in, you know, in one of the subsections, and I was not aware of this question. And this was soon after Dipendra joining IIT. We were having an evening walk, and he asked me whether, you know, this particular coefficient can be explicitly computed in a particular case of interest. So this is like a toy problem in finite groups, but this is a very interesting group in number theory. If you were working with number fields or p-adic fields, you know, this leads to a lot of actual number theory, and doing something for finite fields also might give something interesting in number theory. So maybe that's why one was interested in this question. So the question was, this is a very famous Galvan pair. You take finite field of Q elements, Q is a prime power, and you consider GL2 of FQ, so a simple enough group, and you take the diagonal torus. So this is A comma B embedded diagonally. So A0, 0B sitting inside this. And then one knows that H is a Galvan subgroup of G. That's not difficult, and anyway, it's well known. And you can also take the quadratic extension of FQ. There's a unique quadratic extension. That's a field of cardinality Q square. You take its multiplicative group, that is the group of order Q square minus 1. And there's a natural embedding of K into G. And that also is well known. It's a Galvan subgroup. So there's a good situation where the correlation coefficient defined by Gross can be looked at, can be investigated. So specifically, let me elaborate. G is set of all ABCD, where ABCD are from FQ, and the determinant AD minus BC is non-zero. H is FQ star cross FQ star. That means A0, 0D, where AD is non-zero. A and D are from FQ star. And this is, so you take FQ square and you write FQ square as FQ generated by one element delta. And then anything in FQ square you can write as A plus B delta. Delta will be a trace zero element, where trace from FQ square to FQ. And using that, you know, you can embed K in G as A B delta square BA, where the determinant is again non-zero. So these two are well known to be Galvan subgroups of this G. And you can take a representation of G for which dimension VH we know is less than or equal to 1. So you take a pi such that the dimension is 1, dimension VK is also 1. And then look at these correlation coefficients. So that's a question that we were interested in. And remember, Q is a power of a prime P. So let's fix the prime to be P and some power of P. So let's say P power M. So this is the problem that we are interested in. And this is, I think, from 2012, there was this International Colloquium of Mathematicians at TIFR. I think this photo is from at that time. Or maybe Negroes gave this panorama lecture, so maybe the photo is from that time. Yeah, I think it's panorama lectures. Anyway, beautiful photo. So this is Negroes, and this, of course, many of you know the paper. So our result is, so here is the plain English summary. We are unable to do this. We are unable to compute even in this basic situation of GL2, FQ, and this diagonal torus and this non-split torus. You know, it should be some complex number. You just compute that and it should be some complex number, but we are not able to do this in general. But what we can do is, so up to now, you know, the problem is purely a problem in complex representation theory. There is no Brouwer, there is no p-modular representations here in the question. But what we are able to prove is the following. What we can prove is a modulo p result. So we can compute this. We cannot compute this coefficient in general, but we can do enough theoretically in order to say that though this is a complex number, it is a certain kind of a complex number where reduction mod P makes sense, okay, in a precise way. And it makes sense, so that is the first statement. And if it makes sense, of course, you ask, can you compute that particular value? And that we can do explicitly. Okay, so this is our result. I will state the formal result. This particular thing that we were interested in computing, we cannot compute in general. We can compute given a particular example. We know how to compute it, but not theoretically. We can't do that. But we can say this much, that it is a complex number. You know, complex numbers can be identified with, you have the field of p-adic numbers, and you can take its algebraic closure. And there are these completely uncanonical axiom of choice based identifications between these two fields. You can fix any one such field, and you can think of this as an element in QP bar. And then we claim that it's actually in ZP, p-adic integer, and therefore modulo P makes sense. And then we compute that. So that's the meaning of this English sentence. I'll state it more formally later. Let me also make a slide on what are the basic tools in doing this problem. So you have already saw that, you know, the result is about mod P, which was not part of the question. And this is where, though the question was about ordinary representation theory, we are appealing to Brouwer theory, the third part of Say's book. The question is from the first part of Say's book, so to say, and we are appealing to the third part of Say's book, and we invoke some recent results about P-modular representations in order to get this particular answer to this particular problem. So we convert the problem into, so how do you convert, you know, the reduction mod P of, by P, I mean the P that is there in your left group, right? Left group is GL to FQ. Q is a prime power. It is that P that I am taking. So it is, so P does divide the cardinality. So the modular representation theory is not easy. It's a difficult theory, relatively speaking. And this reduction mod P of representations, again, is not easy, because in characteristic 0, everything is semi-simple. You know, what does that mean? Every representation can be written as direct sum of irreducible representations. These things are not true in P-modular representation theory. Things are far from being semi-simple. So they can be non-trivial extensions. There are all kinds of complications. So it's not at all clear the inner product that you take there. How do you do that here? Anyway, over P, there is no inner product also. Over FP, there's no inner product also. So how do you convert a question about inner product over complex vector spaces to a P-modular problem? There is no obvious way, because there's not even the notion of inner product over FP. Inner product is only over R or C or something. So what we do is we convert the original problem into a problem about characters of complex representation. Character here means the trace of pi g, the second character that I introduced. We convert the problem into a problem in character theory. So this is, you know, Frobenius 1896, who introduced characters. And then we formulate an analogous problem, but we cannot use the word inner product anymore. But having converted the problem into a problem in character theory, via character theory, we can formulate a new problem, an analogous problem for P-modular characters. So this is Brouwer character, Brouwer's famous paper of 1937, where he introduced Brouwer characters. And then we can formulate this analogous problem, and solving this analogous problem in the mod P world, in the characteristic P world, is easy. And I give a one-line philosophical reason for that, which is that, you know, it is a P, what is called a PP case, because P divides the character, P divides the cardinality of your group on the left-hand side. And the characteristic of the vector space of the vector space defined over the field characteristic is also P. So once you have both sides P, representation theory becomes more algebraic. You know, usual complex analysis, I mean, usual complex representation theory, one could have said, you know, there's an element of analysis there, so to say, quote unquote. Whereas this is purely algebraic in the sense of algebraic representations in algebraic geometry. And then, you know, calculations are easier, and we can solve the problem completely, this analogous problem. And now to come back to, but the question was not about P-modular representation. So to come back, there is a relatively recent result, 2007, by Fred Diamond, of reduction mod P of complex representations of GL2FQ. And we make full use of Diamond's results in order to take our solution here in our third bullet point to connect it to the original question. So this is our the way in which we connect these two. So this is a, okay, so these are just plain English sentences, but philosophically this is the underlying, this is the crux of the proof. I'll make one note that that mod P reduction should come handy for this problem. So when you start working on this problem, there are so many hints that maybe you have to take mod P will show up, and this was also suggested by some work of Vinayak Vatsal. That mod P should come in. There are various ways in which one can think, but how to employ this mod P thing is not at all obvious because it's a question about inner product and there's no mod P analog. So what salvaged the situation for us, the key insight was, one can convert it into characters, and characters, there is Brouwer, Nesbit, etc. Characters in characteristic 0 and the Brouwer character, which is also a characteristic 0 object tailored for mod P theory. And these two things are nicely connected. Therefore, you can convert the original problem to a problem that can be converted to mod P theory, and then you can do this association. So that's how we do it. So I will come to the formal statement. Let me go to some more basic things, because in the result, when I state the final result, of course, everyone will understand the final result because, it's a number and I'm giving you the number. So there's nothing more to understand, but there is a little bit of ambiguity the way it is being phrased. So let me try to clarify that ambiguity by a very small example. So FQ is a field of Q elements. Q is some power of a prime number P. And FQ star is the multiplicative group. As you know, it's a cyclic group and its order is Q minus 1, all non-zero numbers. So let me write down the character table in one particular case just to illustrate where the ambiguity can come from. So Q equal to 5. So Q minus 1 is 4. So the field is all fourth roots of unity together with 0 and characteristic as 5. So you can take, one fourth root of unity you fix as I, and then the other fourth root of unity, primitive fourth root of unity is minus I. So if these are your non-zero numbers, then you have the trivial character, then you have the order 4 character, which is 1 goes to 1, I goes to I, minus 1 goes to minus 1, minus I goes to minus I, where this I is just a simple I whose order is 4, and this I is the complex number I. Okay. And I could have written A here, A square here, A cube here, A power 4 is 1, and A going to the complex number I, square root of minus 1. And then its square will be 1 minus 1, 1 minus 1, and its cube will be I cube is minus I. Right? These are all the characters of cyclic group of order 4. Now, the thing to notice is that, there is no way to distinguish I from minus I, right? I is just a symbol for square root of minus 1. Your I could be my minus I. There's absolutely no way to distinguish. You just fix one and then you go ahead in your life, right? That's all that you can do. And therefore, your alpha may be my alpha cube. This much ambiguity, you should allow me. Okay, this is part of the problem. So this is part of the deal, and this will reflect in our results too. This will come in our results, as you will soon see. Here is an interesting aside. Of course, some of the senior people in the audience will know this story. I think it's a very famous story which are shared over coffee table, maybe. But, B. Suri from ISI Bangalore actually has put it in resonance. So I will quote that. So V.S. Varadarajan, famous Lie group theorist who passed away only recently, maybe 2-3 years back, he was in UCLA. Was very, very much influenced by the seminal work of Harishchandra. He was also a scholar of Harishchandra. Maybe he has many his reminiscences of Harishchandra is also frequently quoted, etc. So there's an amusing folklore about this rather deep influence. The influence was so much that Harishchandra had the habit of always saying, we fix an I a square root of minus 1. Many of us may not do that, right? I mean, you just take an I and go ahead. It's all understood. Of course, you are fixing one. But Harishchandra apparently always fixed one very, very formally and clearly. And Varadarajan also used to do so. And on one occasion, M.S. Narasimhan ask Varadarajan if the choice of the square root of -1 was the same as Harishchandra's. Okay, so but this ambiguity is there for us, and so so PGL to FQ. So I'm putting it P here, which means you are going modulo the center. The reason being, though the group is GL to FQ, these dimensions that I am interested in, dimension VH and dimension VK, they are at most one we know. Now we are interested in whether they are equal to 1 and they are non-zero. That is precisely when these representations factor through the center. So they in fact become the representations of PGL to FQ, and all representations of PGL to FQ have this property that the dimension is actually 1. So that means in our problem, it is this group that we have to look at, not the original GL to FQ, because anything that does not factor through the center, there is no question, because then the dimension is 0. So there's no question. There's no VH, there's no non-trivial VH fixed vector. So here is a character table. As I said, the problem becomes a question of character theory. So if one has to do computations, one will have to look at it. But I just thought I will display it here. We are not going to do any computations in today's talk. Let me give, it's a finite list, right? It's a finite group. So there will be finitely many irreducible representations. And as all of us know, number of irreducible representations is a very famous number for any finite group. Number of ordinary complex irreducible representations, it is nothing but the number of conjugacy classes. And there is one more very famous identity, which is also EC, which is that if you take all these irreducible representations, their dimensions, if you square it, and if you add all that, it will be the cardinality of the group. These are two very famous identities. And here are all the representations of PGL to FQ. There are two one-dimensional representations. So you take the character of FQ star, that will be of order Q minus 1, and you take the power Q minus 1 by 2. So this will be an order 2 character. And this order 2 character can be thought of as a character of this group also. So there are exactly two one-dimensional characters, one-dimensional representations. There are two representations of dimension Q. And listing all the irreducible representations. There are two of dimension Q. One is called the Steinberg representation, named after the famous mathematician Richard Steinberg. And then you can also take a character twist of that. So these two are there. Both these are of dimension Q. Then there are what are called principal series representations associated to two characters. One is alpha power R and one is alpha power minus R, the inverse of this character. And these are of dimension Q plus 1. And here you can take R1, 2 up to Q minus 3 by 2. When you take R equal to Q minus 1 by 2, it will not be irreducible and it will lead to Steinberg. And when you continue after Q minus 1 by 2, you have already counted it. That will come as alpha power minus R, alpha R. So you can stop counting till here. So how many are there? These are of dimension Q plus 1. There are Q minus 3 by 2 many. And then there are what are called the cuspidal representations. They are associated to characters of the quadratic extension. And here chi is a character not of FQ star, but FQ square star, the quadratic extension of Q. And here, you should count. So I have written it as Q minus 1 times R, and R will vary from up to Q minus 1 by 2. So there are those many. Let's do a sanity check. I said there are two famous things in basic representation theory, maybe in lecture 3 or lecture 4 of MSc representation theory course, it will be proved that the number of irreducible representations is the number of conjugacy classes, and sum of squares of dimension of irreducible representations is the cardinality of the group. So let's do that sanity check. This is Q minus 1 by 2 plus Q minus 3 by 2 plus 2 plus 2. And that is the total, which is Q plus 2, which is exactly the number of conjugacy classes, as one can check. And sum of squares of dimension will be twice 1 plus twice Q square plus Q minus 3 by 2 times Q plus 1 square plus Q minus 1 by 2 times, these are cuspidals are of dimension Q minus 1 square. And you can do this, and this is Q times Q square minus 1, which is a famous linear algebra exercise. You know that is a cardinality of PGL to FQ. You know that the famous exercise is the cardinality of GL to FQ or GL and FQ, that is Q square minus 1 times Q minus 1 times Q, and you are modding out by the center, which is Q minus 1, so it is Q times Q square minus 1. So that is also true. It is the order of the group. Okay. So these are the representations. So for each of these representations, we should compute the correlation coefficient. And let me formally state the result. And fix any one identification of QP bar with C. QP is the field of periodic numbers. QP bar is one algebraic closure you fix. You identify with C. This is, kind of a useless identification. There's no real field theory which you can do with this identification. There's nothing canonical about it. But in order to state these kind of results, you can make this identification. And you see there is an R here, right? There is an R in principal series and there is an R in cuspidal, where R is ranging through these things. And you have to write this R, you write its periodic expansion. So R is a natural number. R may be 5, 6, 10, 1,000, whatever. You express R in terms of P. And if Q is P power M, they will be at the most P power M minus 1 will come, as you can easily see. Okay, so here I have written Q minus 1 by 2, but what is the periodic expansion of Q minus 1 by 2? It is P minus 1 by 2 plus P minus 1 by 2 times P dot 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 P minus 1 by 2 times P power M minus 1. All the Ri's are P minus 1 by 2. That is Q minus 1 by 2. And in the cuspidal case, you write slightly carefully, you write as 1 plus R naught plus R1P, etc. Just put a 1, subtract 1 and then do the periodic expansion. So get this R. Now the point to note is that these Ri's depend on, so I have suppressed the notation, these Ri's depend on this identification. Because in our proof, these, see what happens is you have a character alpha, which is an ordinary character. And you're going to think of this as a mod P character via this identification. So once you fix alpha, thinking of alpha as a mod P character, you are unknowingly fixing an identification. If you change that identification, your alpha might change. And once your alpha changes, your original character, that power R will change. So in that sense, R is depending on this identification. So fix one. And then you get these Ri's. So Ri's depend on the choice of this identification. And then the theorem is the correlation coefficient belongs to ZP. See, it is in QP bar under this identification. But whatever identification you take, I'm not saying it is in ZP bar. I'm saying it is actually in ZP. So that going modulo the prime number P itself makes sense, not just a prime ideal above P. See, if it was in ZP bar, you can only go modulo a prime ideal above P, and then, there's some ambiguity. Because if you choose some other prime ideal, can you go modulo that, etc. But this actually belongs to ZP. So modulo P, you can go, and then here is a complete answer. So you look at these Ri's, and if each of the Ri is even, so you have M many Ri's, and if each of this Ri is even, then it is this number. It is minus 1 power, it's a particular sign, times R choose R by 2. Each of the Ri is even, in particular R is even. And so R by 2 makes sense. And it is R choose R by 2 times Q minus 1 minus R, choose that number divided by 2. And if one of the Ri is odd, the answer is 0. VH and VK are actually orthogonal. So it's a complete result, but only modulo P. So that's the result. And there is a very famous classical result, which I did not know 3-4 years back, but it's a very famous result in combinatorics with a very beautiful 1-paragraph proof in Wikipedia. Lucas is like 1800s. So it's very old combinatorial result about binomial coefficients. There's a Conduits Theorem, which basically says this, that if you take the periodic expansion, then modulo P, see, this is a huge number. R may be a big number. You can write the periodic expansion of R. And if you are interested in these binomial coefficients only modulo P, then you can take these periodic coefficients and do the appropriate thing and take the product over all the things. This will be a much smaller number. This will be a much bigger number, but they are conjugate modulo P. So therefore, computing this is also not difficult, because you are anyway, asserting only something modulo P. So modulo P, you can make these coefficients much smaller compared to the original coefficient and easily compute it appealing to Lucas theorem. Let me do one example, and this is my last 2 slides. Just one example, just to show how that ambiguity is coming. Let me take Q to be 49 So what is my P? P is 7 and M is 2. And alpha you fix a character. So this also, you know, so once I take so F49 star is a cyclic group of, is the cyclic group, a cyclic group, whatever, the cyclic group of order 48. And its character group is also a cyclic group of order 48, fix a generator. So I'm already fixing something. So that amounts to fixing a primitive 48th root of unity. So already one fixing is involved. And consider this particular principal series alpha power 10, alpha power minus 10. Now the ambiguity is coming in the following way. If alpha is a generator, because 5 is coprime to 48, alpha power 5 is also a generator. So if you change the identification of QP bar and C, it amounts to, in this particular calculation, changing the generators here. So my R here was 10 if I started with this alpha. If I started with this alpha power 5, my R would be 2. So my answer will depend on my R because it's binomial coefficients involving that. And therefore, let us do with this model. If I take this, then I have to write the p-adic expansion of 10. And 10 is 3 plus 1 times 7. It is a 7-adic expansion. And then what would be my theorem? My theorem says, if at least one of the coefficient is odd, answer is 0. So correlation coefficient is 0 modulo 7. So that's a conclusion from the theorem. Okay. So this does not say anything about the original correlation coefficient, right? Some non-zero number can also be 0 mod 7. After all, if this was 7, then it is 0 mod 7, right? So it does not answer the original thing. But you know, I can play around with this. I can take another generator, which amounts to, you know, changing the identification. And I can start with this, and 2 is 2 plus 0 times 7. Now both the coefficients are even. 0 is an even number. Both the coefficients are even. I can apply my theorem. I'm applying by appealing to the Lucas theorem. That's why I have product of two such things. So the first one is for the first coefficient, 2 choose 2 by 2, 2 choose 1, 0 choose 0, which is 1. And p minus 1 by 2 is 3 because p is 7. And similarly for p minus 1 minus r. So that is p minus 1 is 6, 6 minus 2 is 4. 4 divided by 2 is 2, 6 minus 0 is 6, and 6 divided by 2 is 3. So if you do this, the answer is 2 mod 7. So it does depend on the identification that choosing I versus minus I ambiguity can change the answers. And but this is good. This choice is good. It's not a negative, it's a positive, because from this I can conclude, see, our interest is in the original C pi hk as a complex number. Because, you know, under some identification modulo 7, it is 2, which is a non-zero number. Immediately you can conclude that the original complex number is non-zero. It is not orthogonal. From this you could not have concluded, but you use your freedom, adjust the result, and you conclude that the original things are not orthogonal. And the conclusion, this is the original complex number is not 0. And in fact, you know, given a particular example, we have methods in which if you have a long piece of, you know, I mean, these are computations which by pen and paper, it takes, you know, 1 day for one computation. But those who are comfortable with Sage or something, maybe, you know, it's easier to do. So anyway, these kind of things can be done. For 49 is not such a big number, but still it does take a few hours to do this computation on pen and paper. And you can compute that this is actually this particular number. 10 minus root 2 by 150. Here also there is a little bit of ambiguity because I'm fixing a choice of primitive 48th root of unity. If I change that, you know, maybe I will get 10 plus root 2 by 150. So what will happen is, if you change that thing, you know, your set of representations, they will be a permutation. So finally, for a collection of representations that you look at, it's all perfect. And you can see these answers can be nicely explained. See, one answer is 0 and the other answer is 2. Now that in this particular case, you happen to know the real final answer, what is square root of 2 in F7? 2 is a square modulo 7. So there should be 2 square roots. What are they? So 3 is a square root, right? Because 3 square is 9 and 9 mod 7 is 2. If 3 is a square root, then of course the other square root is minus 3, which is 4. And 4 square is 16, which is 14 goes. So that also is 2. So square root of 2 is either 3 or 4, and choice is up to you. You have to fix one. Suppose you choose it to be 3, then what is this? It is 10 minus 3 by 150, which is 7 by 150. And 150 modulo 7 is 2 into 7, 14, 10, 1, 7, so 3. So, but 7 mod 7 is 0. So it is 0 by 3, which is 0, which is giving you this answer. Whereas if you take the other choice, it is root 2 is 4. So 10 minus 4 is 6. And 6 by 3 is 2. And that gives you the other answer. So everything matches perfectly. So there are choices. Answers involve choices. But all these choices match, they are all in perfect harmony. And one can see this in various respects. So this is one part of our results. We have some more results regarding this particular constant, but I think one should not do everything in one talk. So I stop here. Thank you.
Yeah, thank you so much. Yeah, this was a wonderful talk. So any questions from the audience?
Maybe I'll also stop sharing, and if necessary, I can share again.
Yeah.
So these numbers C pi hk,
Yeah.
If one is able to compute them for maybe a large number of h's and k's,
Yeah.
this bunch of numbers, do they actually give some kind of invariant for the representation?
Some kind of?
Invariant for the representation.
No. So no, we are not varying h and k in this particular question. H and k are fixed. We are only varying the representation, and it's a finite set. It's a finite group. There are only finitely many representations, and in theory, one can. I mean, for a small enough thing, one can compute each one. If you have computational machinery, each one of those can be computed, and you will get some number, and one can say that this number will be a complex number. It will be a real positive number between 0 and 1. You are taking modulus, you are taking square. So it's a real number, and one can also see that it is between 0 and 1. And so given a representation, there is one number associated to it. There's only one number. So there's not a set of numbers from which one can conclude something about the representation. Now, maybe you are asking, suppose you are in a situation where there are many other Galvan subgroups also, and then compute all those, and then will they say something? No, I have no idea, because, for example, in this particular case, PGL to FQ, this particular H and this particular K are the only two famous Galvan subgroups. Okay. There may not be such a rich supply of Galvan subgroup given one particular group. What is there in plenty is this triple. There are a lot of famous examples. G, H, K, there are famous examples. But given one G, maybe there are not so many choices for H and K.
Yeah, I was trying to understand whether any information about the representation can be deduced from, maybe if you're able to compute enough of these numbers.
Yeah. But enough of these numbers we don't have. Okay. Because H and K are not in plenty. Given a G. But on the other hand, if you vary everything, if you take the triple G, H, K, where you also vary your G, and therefore you are in a different world, then there are many famous examples of Galvan subgroups, Galvan triple like this. Yeah. But it does say something about the representation, because what I have not done in this lecture is that one can attach to all these representations. So there are only Q plus 2 many representations in this particular group. Each of this representation, one can attach a sign. One can say these are the positive representations and these are the negative representations. Okay. And what is kind of easy to observe is that this particular correlation coefficient will be 0 if the sign is -1. For the so-called negative representations, the answer is automatically 0 without doing all this heavy machinery. But
so the vectors are orthogonal.
Vectors are orthogonal if the sign is -1. But if the sign is +1, then the vectors may be orthogonal, may not be orthogonal, and it becomes complicated. And this is a feature in number theory also. There is what is called a sign for associated to, like modular forms, like Ramanujan delta function kind of objects. And they also have what is called L functions. And whether L functions vanish or not, like Riemann zeta function, whether it vanishes or not at half, right? That kind of a question. if the corresponding sign, so this is purely analogy. There's no obvious connection between this and that. Purely analogy wise, if the corresponding sign is -1, then the L function does vanish at the critical strip. But if the sign is +1, whether the L function vanishes or not is a difficult question. And this is in some sense analogous to that. So we can define an appropriate sign. If the sign is -1, it is easy to show that VH and VK are always orthogonal. If the sign is +1, we don't know whether they are orthogonal or not, and we have these kind of results.
So this was the only reason. I mean, these are both natural Galvan pairs, but is there a bigger picture on why you were interested?
Is there a bigger picture? Is a good question. For example, in GL2 itself, by going above for a field, you can get another famous Galvan pair. But in this particular method, one thing which came very handy in all this mod P reduction stuff is, though your group has cardinality divisible by P, if you look at both the subgroups, H and K, H is Q -1, K is Q +1.
Right.
And both are co-prime to P. So the Brouwer-Nesbitt theory of mod P reduction worked smoothly. Whereas some other famous examples, your subgroups also will have a P in it. So, but we should try. We haven't tried.
Okay. Okay.
In permutation groups also, there must be, in SN, there must be very famous Galvan subgroups. So one
Right,
could
exactly.
try. But the mod P theory also should be well understood. In this particular case, there is Fred Diamond 2007, GL2 FQ. GL3 onwards, we don't understand mod P reduction very well. There are some results of Hersey, but not so complete.
Okay. Any other questions?
Yeah. Is there a way of,
hi.
You are making a lot of choices for the roots and generators and other things.
Yeah.
But is there a way of making it more canonical or whatever?
No, it is inbuilt in the question. It is inbuilt in the question in the sense, suppose, I take, let us take PGL to F7, just to illustrate, okay? So how many principal series are there? 7 minus 3 by 2. So that is 2 principal series.
Okay.
Okay. So which will be, if your generator, if you fix as chi, it will be chi comma chi power 5 and chi square comma chi cube. No, chi square comma chi power 4 and chi comma chi power 5. Now, if you change chi to chi power 5, which is another generator, it is okay. In this case, there's no ambiguity because it's such a small group that it will become chi power 5 comma chi, which is isomorphic to the first one. So there's no ambiguity.
Right.
If you go to 11, if you go to 11, you will see that there will be 3-4 principal series, out of which 2 principal series via character table you cannot distinguish unless you fix. Because your chi will be my chi power, Right. So for the collection of representations, 0 or non-zero is a perfect answer. Even as complex numbers, for example, my 10 minus root 2 will be your 10 plus root 2. Because it depends only on, fixing the primitive root of unity, which anyway,
Yeah, but that's what I'm just wondering whether, is there a way of maybe enlarging the group or a problem or some such thing so that, the choices become part of the data?
So there is one way in which some of the ambiguity can be thrown away, which is that, don't work with complex representations, work with QP bar representations. Then a lot of choices are gone. But then, the result is about QP bar representation.
No, okay. Right. Okay. Yeah. No, I'm saying, yeah. Okay.
So if we state the result, starting with, we are starting with the representation over QP bar, all those things which come from that identification has gone away. But, when we are able to
Right. Then what you're saying is that, the whole thing changes with the identification of QP bar.
And that we are able to make use of.
Okay. So what you're saying is, okay.
If we stated a result for QP bar, this last example that I showed, some complex number is non-zero, you may not be able to conclude because we are changing the identification in order to, get some benefit out of it.
Yeah, no, okay. Right. Oh, very interesting. Yeah. Is there any general conjecture, or as people ask, what is the significance of the C pi HK?
So if we are, okay, it is being recorded, but anyway, I am kind of a bold person. So because it's Rajan there, no, it's okay, it's okay. In fact, if it's fine. So to you and to Deependra, I will always say the following, which is that, see, in finite field representation theory, there is an epsilon factor. There is a root number. There is no L function. L function is there only for p-adic groups and adelic groups, not for finite groups.
Right. L functions in some sense.
There is no useful L function for if you take GL2FQ and if you take a representation. Now, this particular correlation coefficient, some of the other results in our paper which I did not present, there are some results which show that you think of this as the L function. Many of your conjectures, many of your what you would hope for will go through. I'll give you the following thing since you asked this thing. You can consider an extension of finite fields, and you can consider base change. Both of our favorite topic, right? So you take base change, which is well known for finite groups. Also, base changes. Now you consider the correlation coefficient upstairs of the base change representation.
Yes.
And as to answer to Tirtha, I was saying there is a sign that you can put to each of these representations, right? Which is the epsilon factor. Okay, it is very much the epsilon factor. And the easy observation is if epsilon is -1, then this correlation coefficient is 0.
You're saying that.
If sign is +1, we don't know. We have to work. It could be 0, it need not be 0. So this is very much like global root number being -1, L function vanishes at half. Obviously.
Right, but
from the functional equation.
By epsilon, by the root number, you're meaning the root number of pi.
Yes,
which is some normalized value of the Gauss sum or something.
Correct. So, but here epsilon is easier to define, and this correlation coefficient is a totally different looking object. What I'm saying is in the usual automorphic forms, if you have the root number -1 from the functional equation, it follows, take a self-dual, PGL2F. So the L function vanishes at half if root number is -1. If root number is 1, whether L vanishes or not is a complicated question.
Right.
Now, one more thing is, if now you take, in the automorphic situation, not pi, but base change of pi. Okay, let's fix quadratic extension and take base change. Now you take L half of base change of pi. So the functional equation will be root number of the base change of pi times L half of base change of pi. Now, root number can be 1 and still L half can easily vanish. Because the root number downstairs is -1. See, root number upstairs will be root number downstairs times root number downstairs of the quadratic twist. So it can be +1 because it is -1 times -1.
Right.
For this reason also L half can vanish. And we have a theorem in our paper. We analyze the correlation coefficient for the base change and we prove a difficulty. The earlier result that I said, that if the sign is -1, correlation coefficient is 0 is easy. It's a 2-line proof, which comes at the very starting of our paper. But we have a difficult theorem later in the paper, which shows that if you have a base change, if the sign downstairs is -1, then the correlation coefficient of the base change vanishes. Where the sign upstairs is +1.
But no, if you are thinking in terms of L functions and some things as analog, then you can try to. Is there a factorization for the correlation quotient? We tried. No, it's not, because here, there is no complex variable S for you to give more this thing, right? From one number, see, if you give me 6, I have to think of it as 2 times 3 or 2√2 times 3 by √2. It's difficult, but that there should be something. I mean, if this way of thinking is true, perhaps there is something. So what was Gross's motivation for this?
This I don't know, but though, okay, so this is, is it okay, Guhan, if I share screen and show something since a question came?
Yeah,
Because,
sure.
it's something that I don't understand at all. So it's best that I just, quote gross. And in fact, if there are people more interested in physics in the audience, they will appreciate it more. So I should get Gross's paper. You can see my screen, no?
Yeah.
So this is Gross BAMS. So this comes somewhere inside correlation coefficient. So let me section 8, if I remember. And there are, some interesting physics here, which I don't understand. You have to take the groups to be some triple copies of SO3 and sorry. I guess when I share, my key is a bit slower. So he defines a correlation coefficient in section 8 and section 9 is, what is called Ratcha's formula. So this is physics literature. So, there is something, so Deependra told me that when he was doing MSc physics in IIT Kanpur, he had heard these words. So there is a famous Klapsch-Gordon from representation theory. So there is what is called Ratcha-Wigner coefficients in physics. So this comes in physics literature, what is called Ratcha-Wigner coefficients. And this is precisely the correlation. So they do it in their own way. They have, one complicated way of computing these coefficients, but this coincides with the correlation coefficient for these compact groups. B is this particular thing, and H is SO2 embedded diagonally, and I is SO2 cross SO3. So he computes this. I mean, Gross does this, that this actually matches with Ratcha-Wigner coefficients coming in physics. This must be physics of 1960s or something, maybe, or maybe before that.
It must be quantum mechanics,
Yeah. So maybe I can just.
Hey, great. Anand.
Yeah.
Sorry, I'll have to go out, but thanks. We'll get in touch sometime. I'll call you.
Yes. Nice meeting you here also. Yeah.
Okay. I have to go out for some.
Yeah. See you.
Yeah.
Okay.
Thanks. I'll also leave. Sorry, I have to go out for something.
Yeah.
Oh, sorry. My finger is on the camera. Yeah. Okay. Yeah. Thanks. Anand, very nice talk. Very interesting talk.
Yeah. Thank you. Yeah.
Yeah. Okay. Yeah. Great.
You are settled there, no?
No, not